In this video, I'm going to walk you through the topic of bond enthalpy. Bond enthalpy is just literally talking about how much energy it takes to break a bond between two covalently bonded atoms. So if two atoms are sharing with each other, how much energy would it take to go about breaking that bond? But we're going to look at it for the entire overall reaction. So it's also known as bond energy. Those dot structures you learned are very important here. These dot structures do not go away, and you're going to need to use them here in bond enthalpy. So a couple important things before we get into these problems. Anytime you have a bond that is breaking, that's going to be endothermic. Okay, energy is going to need to enter, some form of energy is going to be needed in order to break that bond. All right, anytime a bond forms, that's exothermic. Okay, so energy is given off. So this idea that you might be familiar with from, say, like a biology class where you eat food and then you break the bonds in the food to get energy that you need is kind of false, because when you break bonds, that actually takes energy. It actually costs you energy to break the bonds in the food. But when things rearrange and recombine into new substances and new bonds form, that's when the energy is given off. So you eat the food, you break those bonds, that actually costs you energy. But then as new bonds form, you get more energy back than what it took to break those bonds. So that's how you get energy by eating food. So to do this for a reaction, there's a pretty simple equation. All right, you're going to look at all the energy of the bonds that are broken and subtract it from all the energy of the bonds that are formed. But notice you need the sum of. So it's all the energy of the bonds that are broken. So you add up all the broken, and then you add up all the formed, and then you subtract the two. So that's very important. It's broken minus formed, but all the broken minus all the formed. So here are the steps for doing one of these bond enthalpy problems. I'll walk you through the steps here, but actually doing an example, seeing an example, I think is where it's going to be most helpful. So the first thing you need to do for one of these problems is you got to draw all the dot structures, okay? You have to know what bonds there are, whether they're single, double, triple, so on. So you need to draw the dot structures, all right? And that'll help you see which bonds need to break, which bonds need to form, all right? Then you figure out all the bonds that are broken, you add up all of the broken, figure out the bonds that are going to be formed, you add up or total up all of the formed, and then you subtract broken minus formed. But the key here is you can't miss this last step, right? The amounts of each substance from your actual equation needs to be considered here, and you need to pay attention to them. So we haven't really worked on balancing equations and stuff like that yet, but you will be given the entire balanced equation. You just have to pay attention to the numbers. So if you look in this equation here, these numbers in front tell you how many there are of each substance. Okay, so if there's two of something, you need to realize, okay, well, if I'm breaking a bond in one of the molecules, I'm actually breaking that bond twice because there's two of them. And we'll look at this as we go through examples. So here is a list of all the different bond energies here that you might need to do some of these problems. The good news is you would never ever need to memorize this list. You just use these bond energies in the problem. So you might need to reference back to this or reference back to your notes when you're trying these. So you just need to literally find out what type of bond it is and then look it up. But you do need to pay attention. If it's a single bond versus a double bond or triple bond, that makes it different. So like, for example, a carbon-carbon single bond here is 347, but a carbon-carbon double bond is 614, and it's different from a carbon-carbon triple bond. Typically, the higher the energy, the stronger the bond here. So you'll notice a lot of these double and triple bonds over here are the higher values because these bonds get stronger as you have a double bond or a triple bond. So never need to memorize these, but you will need to reference this to use these in the problems. So this is literally just saying how much energy do you need to break that particular bond between these two atoms. All right, so we're ready to do this for our first example here. We're going to find the change in enthalpy for this reaction, and we have to use those bond energies. So you can see the reaction there. It's 2 hydrogen peroxide breaking down into 2 waters and oxygen. So again, you do got to pay attention to these numbers in front. They are important here when we're doing this. All right, so the first thing we need to do is draw the dot structures for all of these substances. If you know what a dot structure looks like for a particular substance, like if you do it enough times, and you know exactly what it looks like, you can save yourself some time. But if you don't know what it looks like, you have to follow the steps that we went through for doing the dot structures. Okay, so I'll start here with the hydrogen peroxide. We have to go through and do the dot structure. The first thing we need is to total up the number of valence electrons that we have available here. So we know that for each hydrogen, all right, there's one valence electron. All right, there's two hydrogens though in the formula. Plus, for each oxygen, there are 6 valence electrons times 2 oxygens in the formula. So when I total this up here, we get 12 plus 2 is 14. So that means we need to have 14 electrons in our picture when we do this for hydrogen peroxide. So then, carbons or nitrogens in the center, we don't have any. So you put the atom there's less of in the center. Well, if you notice, H2O2, they're both equal. So then you say, okay, well, which one would I put in the center? All right, it can't be the hydrogen. If you put the hydrogen in the center, they're going to bond to each other and they're going to be done because hydrogen can only bond once. So it's got to be the oxygen here in the center. So you'll put both oxygens side by side. They're going to act like your quote unquote center. All right. Definition of covalent, they have to share at least a pair. All right. Whatever's left goes around them. So I got 2 hydrogens. So I'll put 1 on each side. Whoever's next to your center, they have to share at least a pair with the center. And then you have to make everybody happy. Each hydrogen right now is happy. Hydrogen only wants 1 bond or 2 electrons here, 2 valence electrons. So we need to make each of the oxygens happy. So each oxygen needs 4 more to have a total of 8. Remember, if you're wrong, you'll figure it out in a second. So now that I made everybody happy, I go back and I check, and I did reach 14 electrons. So that would be the structure here for hydrogen peroxide. However, you just need to pay attention that there are actually 2 of them according to the balanced equation here. All right, so you don't have just 1 molecule of hydrogen peroxide, you have 2. All right, so this is going to react and form 2 water and oxygen. So same deal, you got to go through the steps, draw your dot structures. You might get to a point where you know exactly what the structure of water looks like or the structure of oxygen, but let's just assume we didn't know that. So we will walk through it here. So same deal, hydrogen has 1 valence electron. There are 2 hydrogens in water. Oxygen has 6 valence electrons, and there is just 1 oxygen. So when I total this up, that means I need to have 8 dots in my picture here for water. Carbons or nitrogens in the center, I don't have any, so I put the atom there's less of in the center. That's oxygen. Whatever's left goes around it, so the 2 hydrogens. They have to share at least a pair with the center here, and then make everybody happy. The hydrogens are happy with just 2. Oxygen needs 4 more to be happy. And then when I check my number, I do have 8, and that matches the number I should have. So that's the structure of water, but again, there are 2 of them. All right, so you do have to pay attention to that. If you're breaking one of the bonds in the water, you're actually breaking 2 of them because there's 2 waters. And then we have O2, so same deal, got to do the dot structure here. So for oxygen, there's 6 valence electrons times 2 oxygen. That means it's got to have 12 valence electrons here. All right, so you only have 2 elements, so they basically have to go side by side. All right, they have to share at least a pair, and then you make everybody happy. So each oxygen needs 8 here to be happy. So when I do this though, okay, I quickly see that I'm over. I'm at 14 electrons. So when I'm over, I have to double or triple up. Well, I'm over by 1 pair, so that means there needs to be a double bond. So I put the double bond in between the 2 oxygens, and then, if you remember here, you eliminate a pair from each of the participants in the double bond. So I have to eliminate a pair of electrons from each of the oxygens, right? So that would be the structure there for O2, and there's only 1 of them. All right, so now that we have the dot structures, we need to figure out the broken bonds here and the formed bonds, okay? So just so you realize, you always break on the left side, on the reactant side. So if you're doing a reaction, the left side is where you always break the bonds, and then you rearrange them and you form new substances on the right side, okay? So that's just how a reaction works. You break the bonds in the reactants and you form the bonds in the products. So as we're doing this here, what I like to do is I like to make a list. So I literally make a list on the left side of the broken, and then I make a list on the right side of the bonds that are going to be formed. And this will help you stay organized. All right. So the first thing you're going to do here is you're literally going to look at which bonds need to be broken on the left side. So you literally just pick a bond and start. So the first thing I notice is here, there's a bond between the hydrogen and the oxygen right here, okay? It's an OH single bond. So that's going to be the need to be the first bond that I break. It's an OH single bond. However, if you notice here, if you pay close attention, there's an OH single bond right here, and then there's another OH single bond right there. So there's actually two OH single bonds in each hydrogen peroxide that need to be broken. However, remember, there are two molecules of hydrogen peroxide. So the OH bonds that are going to be broken, there's actually four of them. There's two in each molecule, but there's two molecules. So that's 2 times 2 is a total of 4. So when you look up the value of an OH single bond on your list, so you do have to go back and reference that bond energy list, it's 467. Okay, so the amount of energy to break an OH single bond is 467, but I got 4 of them, so it's 4 times 467 essentially. All right, do you see any other bonds here on the left side that need to be broken? So if you're looking closely here, you can see there's an OO single bond that needs to be broken. Okay, that's the other bond here that's on the left side. So it's an OO single. All right, there's just one in each molecule, but there's two hydrogen peroxides, so you got two OO singles. And when you look that up on the table, it's 146. Okay, so there are no other bonds to be broken on the left side. You literally just have to look at your dot structures and see, where do I have shared pairs? Those are bonds. All right, so there are no other bonds to break on the left side. Do you need to break all the bonds every single time? Not always. All right, if you look and you say, well, this bond is going to be reformed and it's staying exactly the same, you might not need to break it. But a lot of times it's very helpful just to break and form them all. But sometimes you can't and sometimes you don't need to. All right, so now we're going to be on the form side here. So I can see the first bond here on the form side, and it doesn't matter which bond you pick, but the first bond I see that I need to form is right here. Okay, it's an OH single bond. Okay, and if you realize there's another OH single bond right there. Okay, so each water has two OH single bonds that need to be formed. All right, so the formed bond is going to be OH single, but there's two in each times two waters, so that's a total of 4 here. All right, and the value of that, again, same as the other side, is 467. So it doesn't have to match the other side. In this case, it just did, but that's just what happened here. So are there any other bonds that you need to form on the right side? If you look at this, okay, the only other sharing I see between here, these atoms, are right here. I see this shared double bond between the O's. So that's going to be an OO double bond. Okay, so another bond that I formed here was an OO double. All right, when I look that up on the list, it's going to be 495, and there's only one. All right, there's only one oxygen in your equation, and there's only one of those actually on the right side, so that's the only one I need to list, so it's just 495. So there are no other bonds I need to form. I have all my broken, I have all my formed. Now I just need to make sure that I am adding them up. Okay, so remember, the formula says all the broken minus all the formed. So just pay attention to here to your parentheses when you're plugging these in. So I need to total up all the broken. So it's going to be 4 times 467, all right, plus 2 times 146. That would be all the broken minus, okay, all the formed. So it's going to be minus 4 times 467. All right, plus 495. Remember, you need to total up all the formed. All right, so if you total up all the broken, total up all the formed, and then subtract them, all right, you should get negative 203, and these get units of kilojoules. You could use kilojoules per mole, but for our purposes, kilojoules work. All right, so negative 203 kilojoules. That negative means that this reaction is exothermic. Energy is exiting. All right, and if you remember, we did this reaction when we did the elephant toothpaste demo. If you remember, it was steaming and it felt warm. All right, that was the energy being given off. All right, so when you're doing these problems, draw all the dot structures. All right, figure out which bonds need to be broken and formed, total up all the broken, total up all the formed, and then subtract. Don't forget to use units of kilojoules. All right, so ready to try another example here. You're more than welcome to try this on your own, pause it, and see how you do. But first thing we need to do when we're doing one of these bond enthalpy problems is draw the dot structures, okay? So the first substance I see here in my equation is H2. So you can total up valence electrons and go through it. I mean, unless you know exactly what it's going to look like. So this might be one of the ones that you get pretty familiar with, and you don't need to go through the steps every time, but each hydrogen has one valence electron times two hydrogens. That's going to be a total of two valence electrons here available for your picture. You only have two elements, so they have no choice but to go side by side, share the pair between them, and that's going to be H2. Again, this is a pretty easy one. That's the only way it could work, so that is going to be the dot structure there for H2, right? Plus, now we have CO2. You might remember what CO2 looks like. We did it as an example, but if not, go through your steps. So we have 4 valence electrons for each carbon times 1, plus 6 valence electrons for each oxygen times 2. All right, so that's going to be 12 plus 4, which is 16. So that means I need 16 dots in my picture here for this dot structure, any more or less, and it's wrong. Carbons or nitrogens in the center. So I have a carbon, so it's going to go in the center. Whatever's left goes around him. So there's two oxygens, so one on each side. They have to share at least a pair by definition of covalent. Okay, and then make everybody happy. Carbon needs 4 more in order to have that magic number of 8. Each oxygen needs 6 more in order to have that magic number of 8. So when I do this, I quickly realize when I total up my electrons now, I'm at 20. I'm over by 2 pairs. So that means I either need a triple bond or 2 double bonds. If you remember to honk here, honk 1, 2, 3, 4 says oxygen likes 2 bonds. So I'm going to do a double bond between the carbon and each oxygen. So when I add my first double bond here between that carbon and oxygen, remember you have to go back through and eliminate a pair from each of your participants in the double bond. All right, then you need to add the other double bond in. So you put the other double bond here between this carbon and oxygen, and just like before, you got to go back and eliminate a pair from each of the participants in the double bond. Okay, so that would be the dot structure there for carbon dioxide CO2. If you total it up, you're at 16, you're good. Everybody's happy. All right, the nice part about this reaction is everything in this reaction, there's just one of everything. So you don't have to worry about the amounts here for any of these. So that's pretty good. All right, they're going to form water. We just did water in the previous example, so I'm not going to go through the steps again. All right, you can go back to the previous problem and look. But basically, you're going to have your oxygen in your center, sharing with each of your hydrogens. Okay, single bonds there. And then the last substance here is carbon monoxide. This one's rather interesting. All right, so go through, do your dot structure, follow your steps. So there's 4 valence electrons for each carbon times 1 carbon plus 6 valence electrons for oxygen times 1 gives me a total of 10 electrons that must be in my picture. So I only have 2 elements. The rule says, carbons or nitrogens in the center. Well, there's only 2 elements, so they're both kind of going to act like your center here. All right, by definition of covalent, you're going to share at least a pair, and then you're going to make everybody happy. So carbon needs 6 more to be happy. Oxygen needs 6 more to be happy. All right, when I total it up, all right, I quickly realize here that I'm over. I'm at 14. That means I'm over by 2 pairs. The only thing I can do here is, if I'm over by 2 pairs and I only have 2 elements, I have to put in a triple bond. All right, so when you add in your first extra bond, you got to go back through, and remember, you eliminate a pair from each of your participants here. All right, then you got to go and add in the other bond, and then just like before, you go back and eliminate a pair from each of your participants. All right, this gives each element here that magic number of 8, and it hits that overall total number of 10. But if you notice, what's interesting here is this is an example where hunk is actually broken. All right, carbon typically likes 4 bonds. He very rarely ever has lone pairs. But if you notice here, all right, carbon has 3 bonds and 1 lone pair. Very rare, but it happens. So this would be an example where hunk does not work. Okay, so now we have all our dot structures. We're ready to go through and do our broken and form. So we always break on the left side, on the reactant side. All right, so I'm going to start making my list here of what's going to be broken. And then the formed is always on the right side, always on the product side. So I literally have to start looking here and say, okay, what is going to be the first bond I see that I need to break? Well, I see an H single bond right there. Okay, so I'm going to list that down. I have an HH single bond here, and it's just one of them. So when I look up the HH single bond on your bond energy list, it's going to be 432. All right, and then I look and say, okay, are there any other bonds I see here that need to be broken on the left side? Well, I see this C double bond O in the CO2, but there's also another one, exact same bond right there, C double bond O. So there's a C double bond O that I need to break, but there's two of them. All right, there's only one molecule of CO2, but it has two C double bond O's. So when I look that one up, it's going to be 799. All right, so now if I check myself here on the left side, there are no other bonds, no other shared pairs that need to be broken. So those are the only bonds that need to be broken on the left side. So now I'm ready to do my forming here. All right, so the first thing I say is, okay, what bond do I see on the right side that I want to form? Well, I see an OH single bond in the water, but realize there's actually two in each of the waters here. So I have an OH single, but there's two of them, okay, in each water. So when I look that up on the table, the value of an OH single is 467. All right, and then I say, okay, are there any other bonds here that I need to form on the right side? Right there, a CO triple bond. Okay, there's just one of them. When I look that up on the list, it's 1074. All right, there are no other bonds that I need to form on the right side. So now I'm ready to do my totaling here. Remember, you need to total it all up. All the broken added up, all the formed added up, and then subtract. So it's going to be 432, all right, plus 2 times 799. Again, watch your parentheses here. You're totaling up all the broken, and then you're going to subtract here from all of the formed added up. So it's going to be 2 times 467 plus the 1074. All right, all the broken minus all the formed. And when you do your math here, all right, if you're careful with your parentheses, it should come out to be 22 kilojoules. Remember, you need units of kilojoules for these. All right, this one's positive, so that indicates here that this is going to be endothermic. All right, energy is going to be absorbed. This reaction would actually take energy in. So follow your steps, take your time with these problems. They do take a little bit of time to do, and you got to pay attention to all the bonds. All right, we're going to try another example. Again, feel free to pause, try this on your own, and then see how you do. But same deals, the other examples, you got to go through and do the dot structures first. All right, so the first substance I see here is CO. I just did that in the previous example. You can follow your steps for doing the dot structure, but we basically know now what it's going to look like. So we're going to have the carbon, all right, with a triple bond here to the oxygen. All right, if you follow your steps, you would arrive at that exact same structure as well. Since we just did it, I'm going to save time. All right, then the next substance here, H2, we did this one as well. I said it's one of the easier ones. If you know it, just, do it. So there's going to be two of them, but it's going to be an H, single H here. All right, so like I said, you'll do some of these enough that you'll just know exactly what they look like. But the last substance here, the CH3OH, all right, that's new here. We want to make sure we can do this. So we're going to go through the steps here to do the dot structure. So the first thing I notice is, all right, I have carbon. So there's 4 valence electrons for each carbon times 1 carbon. Plus, next I see hydrogen. There's 1 valence electron for each hydrogen. And this is something here where, it doesn't matter if you do it this way or not, but I notice there are 3 hydrogens here, all right? But there's also another hydrogen down there. So I'm just going to do it as 4 total hydrogen. All right, if you missed it, you would still catch it as you were moving through doing each element on its own, but I like to group them together. So there's one valence electron for each hydrogen, but this formula has 4 hydrogens. There's a reason why they're writing it like this, and we're going to talk about that in a little bit. All right, so just pay attention to that. There is a reason why it's grouped OH and not the H's all together here. All right, so I still have one more element. I have oxygen, which has 6 valence electrons, and there's just one. So when I total this all up, I got 14 total valence electrons here. All right, so when I do my picture, I need to have 14 dots. All right, so your steps say carbons or nitrogens in the center. So I have a carbon, so that's going to be in the center. All right, and then it says whatever's left goes around it. Well, I have 3 hydrogens remaining, and then this O and H. All right, the reason why that OH is written like that, it's trying to show you how this OH is kind of attached here. It's kind of giving you a hint. All right, it's trying to show you that, look, that extra H is actually attached to the O. All right, so you have your 3 hydrogens remaining, so you can put them evenly around your center here, but then that OH, right, the reason why it's written like that is because it's trying to show you that the O is going to be attached to the center and the H is going to be attached to the O. All right, so whoever's next to the center has to share at least a pair with the center. So each of these hydrogens were next to your center. And then this oxygen was next to the center, so he's got to share a pair. But then the O and the H are next to each other. They're actually sharing a pair as well. So if you ever see that OH written like that in a molecule here, it's trying to show you that the O is probably going to be attached to the center, and then the H is going to be attached to the O with a single shared pair. All right, so now you still need to go through and make everybody happy. All right, if you look at your picture here, carbon has 8 around him. He's happy. Each hydrogen is happy with 2, but the oxygen is not happy with 4. So not each oxygen, the only oxygen here needs to get 2 more pairs. So for a total of 4 electrons. So now when I total this up, okay, I have 14 electrons. So I hit my number. Everybody in your picture is happy. That is what the structure of CH3OH would look like. Again, watch the way they're written. Sometimes they can key you in on how they actually are going to be arranged here. All right, so now I'm ready to do my broken and formed. Remember, we always break on the left side, on the reactant side. So I'll start making my list here of broken. All right, and I'll make my formed list on the product side. All right, so the first bond that I see here on the left side that I need to break is this C triple bond O here. All right, C triple bond O, there's just one of them. When I look that value up, all right, it's going to be 1,074. All right, the next bond I see here on the left side that I need to break is this shared pair between the H's. So it's an H single here, but there are 2 of them. Remember, there are 2 molecules of H2 in your overall balanced equation. So there's 2 of them. When I look that value up, it's 432. All right, there are no other bonds that I need to break on the left side. So now I'm ready to move over to my forming side. You just got to be careful here. Sometimes when these dot structures get a little more complicated, you want to make sure that you're not missing any bonds. So the first bond I see is this CH single bond right here, okay? But you need to realize there's a CH single bond here, and there's another CH single bond right there, all right? So when I do this, all right, I'm forming a CH single, but there's going to be 3 of them. So when you look that up on your list, okay, it's going to be 413. So each CH single is 413, but there are 3 of them. All right, so you say, okay, what other bonds do I see? Well, I see a CO single bond right there. So I have a CO single bond, but there's just one of them that's going to form. So when I look that up on my list, that's 358. All right, and then are there any other bonds that you're forming? Well, yeah, there's an OH single bond right there. So I have an OH single bond forming. All right, when I look up that value, it's going to be 467. There's just one of them. So just double check, make sure you got all the bonds, all the shared pairs there that did form. All right, and now you're ready to do all of your totaling up here. So remember, when we do this here, it's all the broken minus all the formed. Okay, so you got to add up all the broken first. So I have the 1,074 plus 2 times 432. Okay, you got to add those all up first, minus all of the formed. So it's going to be 3 times 413 plus 358 plus 467. All right, all the broken added up minus all the formed added up. All right, when you do your subtracting here, should come out to be negative 126 kilojoules. All right, remember you need your kilojoules here. This is negative, so this would indicate that this reaction is exothermic. So before we're done here, I just wanted to show you an example of where sometimes you might not know exactly um, all the bonds that are actually taking place here in a substance. Maybe it's some type of notation you don't understand. Um, so I want you to see that you don't always need to break and form everything. It's kind of like a little puzzle. You can look at um, both sides of the reaction and see actually which bonds are breaking and which bonds are forming, and you might not need to break and form everything. So in this example, it's telling you that this compound, ethyl butanoate, all right, is actually produced according to this reaction. So they gave you the reaction, and you can see it looks a little bit complicated, and I can tell you, you don't need to go through and break and form everything, all right? If I look here on the left side of the reaction, I look for similarities and differences, all right? So the first thing I notice here on the left, comparable to the right side, is I see this string of CH3, CH2, CH2, all right, C, and then double bond O, all right? So if I notice on the right side, I see that exact same portion here, all right? CH3, CH2, CH2, C with a double bond to the O. So if it's the same thing on the left and the right, that means I don't need to touch it. I don't need to worry about that. All right. There's no sense in breaking it only to reform it. All right. So I do notice though something is different here. I see this C here that has this double bond O. It's attached to an O, but then that O is attached to just an H. Over here, this C with this double bond O is attached to an O and then something different. It's not attached to an H. All right. So in my head, I'm saying, okay, this is the first bond I see here that I know on the left side, I have to break that bond. Okay. I need to get that H off of there. All right. So that means on the right side, this bond right here is going to need to form, okay, because that wasn't there on the left side. So then again, I can look at my picture here and say, okay, well, on the right side, where did this CH2, CH3 come from then that's going to attach to the O? Well, if you look on the left, you say, oh, look, here it is. Okay, so this tells me on the left side that I'm going to need to break this bond right there, okay, because I need this CH2CH3 to be able to add on to the O on the right side, all right? So if I start making my list here of my broken on the left side, I see that I have an O single H that I need to break, all right? And then I also see I have a C single O, all right, from right here that I need to break. Okay, and if you start making your formed list here, all right, we already identified that I need to form that C single O, all right, that's the one right there that we need to form. And then you say, okay, well, wait, what about this substance over here? Where is this coming from? Okay, so we need to pay attention to that as well. So remember, on the left side, you broke off this H right there, and you also broke off this OH right there. Well, they're going to come together and combine, and they're going to form the water over here. So you have this bond right there being formed, this O single H. Okay, so again, this is like a puzzle. You have to look on the left side and say, okay, you know, what's actually going to be broken? What's going to be formed on the right? But what's the same? And then how does this kind of all work together? So after I did this, if you notice, all right, I cut off this H right here. I cut this bond right there. But then on this side, those substances, those pieces kind of come together to form your new substances here on the right side. So before I even do any math, I can see here there's nothing else to break or form. Notice The bonds that you're breaking on the left side are exactly the ones that are forming on the right side. So this would have an overall change of 0 kilojoules. Okay. Now, don't think they're all going to have an overall change of 0 kilojoules, right? But I just want you to see here an example where, all right, you might not need to break and form everything. If you can do a problem and leave some things the same because they're going to be the same on both sides, you can do that. All right. So if a bond doesn't need to be broken, don't feel that you need to break it. And there are going to be examples where you have no choice but to only break and form the bonds that need to be broken.